Hi guys, so today we're going to be having a look at these Visico VC100 LED studio lights. A good friend of mine uses them for his video work. Unfortunately, this specific one overheats after about 15 minutes of use, and it becomes completely, it just goes dark, it goes dead. There's no other action that takes place. This specific model is about 13,000 lumens at 1 meter. I measured it at 100 millimeters. That's about 220 kilolux. Really quite bright, these lights. Yeah, after about 15 minutes, this specific one cuts out on its highest setting. So let's open it up and see what exactly the problem is. Luckily, we've got another one that we can compare temperatures and settings with. So let's go. Right, this is a big beast. It weighs about 2.5 kilograms. It has a fan at the back here. Yeah, you can actually hear the fan turn on right from the start. It actually sucks air, cool air in from this side, passes it through, and then blows it out through the front heat sinks next to the LED element. So here's the view from the front. Let's actually have a quick look at the element up close. You can see it's made up of quite a few LED elements. Now, I don't know if you can make that out. The documentation says there are about 500 individual LED elements in this LED array, which produces the 13,000 lux at 1 meter. And then at the back it's got just the 220 volt inlet, power switch, a setting that you can use to adjust the brightness. It's got 6 levels of brightness, which it then just displays on that little LED display there. Now you can see it actually has quite a substantial heatsink, a lot of copper here to interface with the back of the LED array, and a fairly large heatsink. I suspect this heatsink probably goes down quite some ways to get rid of the excess heat that's generated by this LED array. And a nice bit of attention to detail here with the grounding strap just to the front of this metal part. Now the challenge is going to be to open this lamp and still be able to switch it on, so that one could have a better look at the exact thermal properties and see what's heating up and what's not. Right, now this whole thing should slide out. There we go, we're in. So it's a fairly straightforward design. The heatsink right at the front, a fan just behind it to push the cold air from the back of the unit out to the front, the power supply section, and then right at the back you've got the control panel section with the various controls and the LED display unit. And there you can see 150 watt power supply, 33 volts DC at 4.5 amps. This is undoubtedly a switch mode power supply, so we'll just have to open it up and see what exactly is going on the inside. Now if you look at the construction, it's a little bit, the whole thing is soldered together, so it's going to be quite difficult to actually troubleshoot this thing while applying some power to it. Alright, so we should be able to just undo these screws, 2 over this side and 2 over that side, and then we should be able to just lift this top part of the heatsink off from the power supply. And we're in again, and the supply actually looks reasonably well constructed. You can see the sill pads on the top of the transformers here, maybe just to bleed some of the excess heat away into the top heatsink. And immediately something else I see is there that looks for all the world to be some sort of temperature sensor. So that's what we'll be interested in when we start diagnosing the problems on the lamp. But let's just quickly have a look at some of the other circuitry and things. What you see here, these are the sort of the feedback wires that come from the rear panel to indicate what voltage must be output to the front heatsink. Over there you can see the output going to the LED element. Interestingly, the power to the rear control board also comes from the same output socket. So that's actually quite interesting. It means that the varying power levels that is being sent towards the front element is also being sent back to the rear controlling board. Interestingly enough, there are two shunt resistors, probably just to monitor the current output, and it's likely that it will also shut down in case of an overload. I don't know if you can make that out, but there you can see the caps, Nichicon brand, top quality caps, really a good thing, rated for 105 degrees Celsius. And is that a date code right down there, the 17th of April 2013. Now that is quite interesting. So the output of the front power supply goes to this little rear board and then gets regulated by that LM2575 regulator. Now if this power supply is operating at full tilt, that's what was it, 33 volts, it means that this little regulator has to dissipate quite a lot of energy in order to down regulate to I'm assuming to the 5 volt that the little control board needs. And it could also be that that is the circuit that is cutting out and not actually the power supply itself. Alright, so I've got 3 temperature monitoring stations going here, or 3 temperature probes going. The top one here that monitors the temperature of the LED element heatsink. The bottom one over here, T2, that monitors the temperature of the 5 volt regulator, just to see if that's causing any issues. And then over here we've got the temperature of the external heatsink of the switch mode power supply. So I think let's switch it on and see which temperature rises. Well, there's a lesson for you. It looks like I blew up my digital thermometer. The two temperature inputs, it seems, are not electrically isolated, and the ground of the LED array and the top part of the little regulator are not electrically isolated either. And it seems when I turned on this light, I blew some circuitry inside my thermometer. So we'll just have to be able to carry on with this crusty little temperature sensor, and also maybe my little IR thermometer. Alright, I'm calling it. It's been about 2 hours now, maximum of about 44 degrees Celsius reached. So I think let's close the case and see if we can solve the ventilation problem. So while it's running, let's probe the output voltage of the power supply. There we go, so currently running at 28 volts. Something else I've only noticed now is that tucked away in between the bent fins of this heatsink, right over there, there's another component, probably another thermal cutout component. So that's an additional indication that we need to have a look maybe at the actual cooling of the entire system. Maybe force some additional air through so that the cooling for the entire system is a lot better than it is at the moment. Okay, I've unplugged the fan, so let's see if we can see what the cutout temperature is of this component right here at the front, this one over here. There we go. At 76 degrees, just over 76 degrees, it reached thermal cutoff point. So that's where the front element basically cut off. That's very interesting. So let's see if we can focus on that and see if there are any other thermal cutouts that we need to attend to. So let's quickly assess. We've investigated a few of the thermal cutout components. One situated inside the switch mode power supply itself, nestled right up to the edge of this heatsink. We've investigated the little down converter, the buck converter, which is definitely not an issue. And then finally, we've seen there is an additional cutout component here. Now, thinking back, when I first tested this device, everything kept on running except the light just cut out. So if the power still was on, but the light cut out, then it means that this switch mode power supply was still running fine. So that tells me that the component on the inside here was not responsible for raising a temperature alert, and therefore this power supply wasn't cutting out. So it seems that we definitely have to just focus on this component here. It seems to me that this component is sort of almost just right on the edge of cutting out under normal operating temperatures. So what I'm actually thinking of doing is, instead of changing this component or maybe fiddling with something here, is to just add just a little bit more ventilation. Basically, the venting slots for this system are only these ones over here. The LED element fills up this space, and the reflector flange fits in here. So there's really only these little slots where it can be pushed out through. So I'm going to add some additional ventilation, drilling some additional holes in this front plate, and then we're going to run another test and see if it's still tripping out. So with a whole bunch of new ventilation holes, I think we can put the whole shebang together again. Alright, ready for some testing. Oh, forgot the mounting bracket. Ah. Alright, I am almost ready to give up. However, I did notice in this specific unit's counterpart, the second lamp that I have here, the fan starts to spin faster and faster the longer it's turned on. So I think it's time to open up the second one, have a look inside, and see if there are any specific differences that we can detect. Right, so I've got the two side by side. I'll let them run for about 10 to 15 minutes, and then we can start comparing some temperatures at various locations. Lexi, are you waiting for us? Yeah. Well, I think as soon as our lucky charm arrived, I might have found the difference. Can you spot it? This fan has got a temperature sensor over there. This one is quite substantially missing a temperature sensor. In fact, it's completely gone. I have no idea where it went. It almost looks like it's been cut out. And also this fan has seen a little bit of wear. So yeah, I'm not too sure what exactly happened there. But that's definitely the problem. This fan is the one that doesn't spin up faster and faster as the temperature increases, but this one does. So we either have to find a temperature sensor for this fan, or we might have to just hardwire it to let it spin faster by default. So now the question is, why was that component cut out? Was this fan salvaged, or was the component cut out perhaps because the temperature control circuitry inside the fan wasn't working? So there I've got it hooked up to my multimeter, just measuring resistance, and let's see if we heat it up a bit. I've just got my little soldering iron here. There we go. Very quickly jumps to 4.5 kilo ohms when being heated, so that means it's a negative temperature coefficient thermistor. And let's see what happens if we cool it. Yo, very fast reacting. And through the magic of YouTube, here is the newly ordered NTC thermistor. This is a 4.7 kilo ohm thermistor. It's the only one that I could find that's more or less close to the 5.6 kilo ohm of the other fan. I think this will suffice. Let's put it in. Now I should be able to just scrape off the top to expose the actual copper of the tracks, and then we can actually just solder the sensor directly onto these pads. I don't have to go try and solder deep inside the fan. Alright, so let's give it a quick test run before we glue it down. Just going to turn the light on. I don't know if you can hear the rate at which that fan is spinning. I'm just going to bring my soldering iron a little bit closer. There we got it. You hear it spinning up? It's spinning really fast now. I'd say we've got a winner there. Right, let's glue it down and put the whole thing back together. I think she's right as rain. Reassembly time. Alright, so let's see what she does. Alright, so this light's been running for about an hour now. Still no problems. It ramps up slightly faster than the other one due to the fact that the thermistor is of a lower value, but at the end of the day they both have the same noise profile. Right, I think I'm going to call this one fixed. If you like these kinds of videos, please remember to give this one a nice big thumbs up, and then I'll see you next time.